Hi, Astronomy. Mr. Janowski here. This is the first slide in Chapter 3, and this is all about physics. So this is Sir Isaac Newton, or How I Learned to Stop Worrying and Love the Physics. So this particular slide, I spent way too much time making this slide. It serves no purpose. It's a reference to Dr. Strangelove, or How I Learned to Stop Worrying and Love the Bomb. Great Stanley Kubrick movie, but that doesn't have anything to do with anything. So here we go. Chapter 3, Gravity and Motion. This chapter is like a crash course in physics. So we have this idea in physics called mechanical equilibrium. What does mechanical equilibrium mean? Mechanical equilibrium is a state of steadiness. It is a state wherein no physical changes occur. It is a state of steadiness. So the fact that things are steady does not necessarily mean that the objects aren't moving. You can be moving steadily, and that would be mechanical equilibrium. What it means is that if your object is moving, its motion is not changing. So ultimately, that means straight line, constant speed. So this does not necessarily mean that there are no forces on the object. Forces change the motion of an object. So you would think if there are forces, well, it must not be in equilibrium. No, you can have forces on the object. You can have forces on the object. What it means is that there is no net force on the object. So the total amount of forces on the object is zero. So we have this thing called the equilibrium rule. Whenever the net force on an object is zero, the object is in mechanical equilibrium, and vice versa. Whenever the object is in mechanical equilibrium, that means the net force on the object must be zero. So net force is equal to F sub net. This is how we write things in math and science with subscripts. Often there are situations where more than one force is acting on an object at a time, and we'll need to figure out the net force. So what is net? If, for example, you were to buy $5 of lemons and $1 of sugar, and now you're going to go sell lemonade, so you do that, you sell $20 of lemonade, how much did you net? Well, you didn't net 5 plus 1 plus 20 equals 26. What you netted was $14. So the $5, that was an expense. I made a negative. The $1, that was an expense. So minus $5 plus minus $1 plus $20 gives you $14. It's the same idea with forces. The net force, you're going to add up all the forces, but you have to respect which way they're going, which is what I have written right there. So net force is equal to F sub net is equal to this symbol F. So what is this funny symbol? This is the capital Greek letter sigma. So this is the Greek version of the letter S. In math and physics, sigma means sum. Sigma S, sum S. That's why we use it that way. So with force problems, it makes the most sense to write sigma F. So imagine you have a box. So we've got a gray box here in the middle. Alice is pulling to the left with 20 newtons. Billy is pulling to the left with 10 newtons. And Charlie is pulling to the right with 18 newtons. So what is the net force on the box? You could write it this way. Sigma F is equal to F sub Alice plus F sub Billy plus F sub Charlie. So we're adding them all up, but when we add them, we have to respect which way they're going. And the fact that Alice and Billy are pulling to the left means we give them negative numbers. And the fact that Billy is pulling to the right means we give him a positive number. So if you add up minus 20 newtons and minus 10 newtons and 18 newtons, you end up with minus 12 newtons, which is another way of saying 12 newtons to the left. When we do this, the convention is left is negative, right is positive, down is negative, up is positive. That's how we do this. So with what force would Charlie need to pull to balance the others? If Charlie were pulling with 30 newtons to the right, that would balance them out, and there would be no net force in this box. So we have an astronomy student sitting motionless in her seat. She is in mechanical equilibrium. So what are the forces acting on her? There would be two, at least two that we care about here. There is a force due to gravity. That's what everyone realizes. Yeah, there's gravity pulling her downwards. And there's what's called the normal force. So anytime two things are in contact with each other, there's what is called a normal force between them. And the normal force from the chair on the student is pushing her upwards. So we have two forces on the student, and forces cause changes in motion, but there is no change in motion here. She is in equilibrium. She's not moving, and she continues not to move. So what's going on? Well, it turns out the sum of the forces in this case will be zero. The amount of force going up is equal to the amount of force going down. So even though neither force is zero, they just cancel out. So the net force, sigma F, is zero. So she's in equilibrium. No change in motion. She's sitting there. She just continues to sit there. So here we get to Aristotle, which in physics I refer to him as Mr. Misconception. So last chapter, Aristotle was kind of a good guy. He figured out two evidence-based arguments that show that the Earth was round. So last chapter we liked him. In this chapter, which is about physics, we don't like him because he had a lot of bad, wrong ideas about physics, and we wouldn't even talk about them at all, except that, unfortunately, they kind of dominated everyone's thoughts about the subject of physics for 1,500 years, 1,800 years, a really long time. So, anyhow, according to Aristotle, motion was either natural or violent. And those words have particular meanings in this case. So, natural motion, let's start with that one. Aristotle thought that it was natural for boulders to fall and for smoke to rise because things seek their natural resting place. So, according to Aristotle, if you pick up a boulder and you let go of it, it goes down. Well, he's right about that. The boulder would go down. But he was wrong about the reason. He thought it was just in the nature of boulders to be down. They're heavy things, and heavy things want to be down on the ground. So if you pick it up and let it go, it goes down. It's not how things work, but that's what he thought. Smoke, on the other hand, if you light a fire, smoke goes up because, according to Aristotle, it's just in the nature of smoke to be up. And they wouldn't have had, helium-filled mylar balloons in Aristotle's day, but if they did, and you let go of the helium balloon, it would rise. Aristotle says, well, that's in the nature of the balloon to be up. This is not correct, but this is what he thought. The other type of motion, according to him, was violent motion. So violent motion would be better called imposed motion, but everyone calls it violent motion, so I'm sticking with that. So according to Aristotle, violent motion is any motion that was imposed by an outside cause. So it's not in the nature of the thing to have this motion. This motion is being imposed on it. So, for example, a cart being pulled by a horse. Well, the cart by itself is a heavy thing. Heavy things just want to sit there on the ground. That's their nature. So if this cart is going to move, you need the horse to impose violent motion on it. That's what he thinks. Same deal with a ship. If you have a ship out on the water, well, it's in its nature to just sit there and float. If the ship is going to go anywhere, it takes wind to push on the sails to make the ship move. So this is what he thought. This is all wrong, but this is what he thought. So now more to astronomy in particular. So Aristotle believed that circular motion was natural for heavenly bodies. So he would have been geocentric. He would have thought the Earth was at the center and everything goes around the Earth. So he would think the moon goes around the Earth. He's actually right. That is true. But he also thought the sun went around the Earth. That's wrong. He thought all the planets went around the Earth. That's wrong. But anyhow, how would he explain the motion that he thought was happening? He would say, well, all the heavenly bodies, the moon, the planets, the sun, all the stars, they go around the Earth in circles because that's just in their nature. They're heavenly bodies. They just like circles. They do circles because that's in their nature. And he says there is no need for violent forces to cause this motion. No, this motion just happens naturally, according to Aristotle. So again, all these ideas are wrong. I'm only telling you these ideas because for almost 2,000 years, people believed them. Everyone liked Aristotle's idea. And for 2,000 years, if you wanted to prove your idea, what you would do is you would compare your idea to the ideas of Aristotle. And if you could make your ideas line up with Aristotle's idea, everyone said that, yeah, you proved it, which is a terrible way to do science. That's called proof by authority. That's idiotic. Don't do proof by authority, children. So then we go to Galileo. Galileo was concerned with how things move, not why things moved, meaning he would actually watch things move and describe what was happening. That's the how things move part, not why things move. He didn't sit there and wonder about their nature and their quintessence and weird things like that. No, he actually, all right, let's make things move and observe what happens. So Galileo disproved Aristotle's idea that a force is required to keep an object moving. He believed that experiment and not logic was the best test of knowledge. And we, as modern scientists, agree with him. You have to do the experiment. And then in class, we watched this Richard Feynman video, which I like this video very much. This is what he said in the video. This video, I'll just go through it very quickly. I don't want to go into great detail, but this short little video, it's only about a minute long, he sums up the entire scientific method, and he does it very well. So if you're going to do something, you make a hypothesis, you make calculations based on that hypothesis, and then you run an experiment. You have to check your idea against the universe. And then the thing in bold is the key idea. If it disagrees with experiment, it's wrong. That is how science works. You have to check your ideas against the universe, and if the universe tells you your idea is wrong, that's it. It's wrong. And that simple statement is the key to science. It doesn't make any difference how beautiful your guess is, how smart you are, who made the guess, or what his name is. So we don't do proof by authority in science. We check our ideas against the universe, and if the universe says you were wrong, then you were wrong. And that's all there is to it. I love that idea. Back to Galileo. So Galileo was, we talked about his ideas in astronomy last chapter, in chapter 2. Now we're talking about his ideas of motion. So he tested these ideas by rolling balls along ramps tilted at different angles. So if you look at this first picture, you'll see the ball rolls down the ramp, speeds up, cruises across the middle, and then rolls back up the other ramp. And he noticed something curious. If he could ignore friction and air resistance, he lets the ball go, it will rise back up to the same height from which you let it go. So that was neat. And that is true even if you change the second ramp a little bit. So now this ramp is less tilted, ball rolls down, speeding up as it goes down, cruises across the middle, slows down as it goes up. And either way, it comes back to the same height, which is very cool. But that's not the important part for us. We're actually most interested in what's happening in the middle. In the middle, the ball just goes in a straight line at a constant speed. And Galileo realized you could make that middle part as long or as short as you want. It doesn't matter because the ball is only going to cruise in the middle, straight line, constant speed across that middle flat part because there's no net force in it. So its motion doesn't change. Once it gets to the flat part, it's got a speed and it's moving in a direction. So if you put no net force on it, it just goes that speed in that direction and nothing changes until it gets to the other ramp. And then things start to change. So this is what disproved Aristotle's idea that a force is required to keep an object moving. So Galileo argued that only when friction is present, as it usually is a force needed to keep an object moving. So yeah, we live in a world full of friction, and that's what makes Aristotle's ideas seem kind of intuitively correct, but when you actually really start studying the motion, they're wrong. So this is the idea of inertia, which is the tendency of a body at rest to remain at rest, and the tendency of a body in motion to keep moving in a straight line at a constant speed. So inertia is laziness. It is the resistance that an object exhibits in response to any effort made to start it, stop it, or otherwise change its state of motion. So basically, whatever the object was doing, its inertia makes it want to keep doing that. If it wasn't moving, it wants to continue to not move. If it is moving and you don't put any outside force on it, it will keep moving in the same way, meaning it will go in a straight line, constant speed. And that won't change until you start putting unbalanced net forces on it. Then we get to Newton. So Newton comes along. Newton is probably the most important scientist of all time. This chapter is really mostly about the ideas of Newton. So he did lots of different things. We're going to start with his 3 laws of motion. And his first law, which is often called the law of inertia, is just Galileo's idea. So Galileo died in 1642. Newton was born in 1642. I don't know, physics teachers like bringing that up for some reason. And Newton's first law is just Galileo's idea of inertia. He just rephrased it a little bit differently. So according to Newton, every object continues in a state of rest unless acted on by a non-zero net force, or every object continues in a state of uniform speed in a straight line unless acted on by a non-zero net force. So if it's not moving and there's no net force, it continues to not move. If it is moving and there's no net force, it moves straight line, constant speed. So different consequences of this. If you have 2 forces on a thing, but those forces cancel, you have no net force. So if the thing's not moving, it will continue to not move. If the thing is already moving, like the ball in the middle part of Galileo's experiment, and there's no net force, how will it move? It will continue to move in a straight line at a constant speed. So the flip of this is if it is not moving in a straight line at a constant speed, then there has to be a net force on it. So no net force, you get straight line constant speed. Well, if you're not getting straight line constant speed, there must be a net force. So in this case, this young lady in the green t-shirt, we will call her Alice, is swinging a mass over her head on a string. So the mass is moving maybe at a constant speed. Maybe she's moving it so that it goes at the same rate the whole time, but it's not going in a straight line. So that means its motion is changing. There has to be a force. So what is providing the force? It's the string. The string is pulling on the ball. The string is making the ball change. Um, Now, Alice is causing the string to do that, but Alice is not directly touching the ball, so it's really the string that's doing it to the ball. So now we're looking at Alice from overhead. She's swinging this thing around. So this thing is going around counterclockwise. When it gets back to this point here, the string is going to break. So which way will the ball go once the string breaks? Will it continue straight line in this direction? Will it continue to curve the way it was doing when the string was there? Or will it shoot out in direction C? And the answer is A. The mass will follow path A. So the mass is going around. So maybe constant speed, but definitely not straight line. Because the string is exerting a force on it and causing its motion to change. It's changing the direction, if not necessarily the speed. So it's changing its direction. At this point, all of a sudden, the ball is moving to the left, and the string was there. It was going to make it curve, down here towards B, but the string broke. So the ball was already moving. You take away the force on it, so now it moves straight line, constant speed. Path A. B and C are wrong. Some people think it would be B. The ball will continue to curve, kind of as if it remembered that it was curving. It had curving motion before, so that some people think, well, that needs to be retained in some way, but it doesn't. And other people say, well, if the string was pulling it in, all of a sudden the string disappears. Well, then it must go out. So they would think it goes in C, but that's wrong too. The answer again is A. So yeah, that was just a mass on a string that you could do, just in your living room. Same exact thing is happening with the planets going around the sun. So the planets are moving. So here's Earth moving around here, the nice blue one. So it's going roughly a constant speed. It does change a little bit because of Kepler's second law of orbital motion. But basically, if it were a circle, it would be a constant speed. But it's not going in a straight line. Its motion is curved. So that means there must be a force causing this motion. That force is gravity. Aristotle said, no, things just move in circles because they like circles. That's in their nature to be doing circles. Aristotle was wrong. Once you know the physics that Galileo and Newton figured out, you know there has to be a force, and in this case, that force is gravity. So then we did a little demonstration with the tablecloth trick. So I'll put these videos in the description. I'll put links to these videos in the description to my own video. The kind of matter of fact one at the top, the tablecloth trick, and then the very exciting David Ginn one at the bottom with his rabbit. I forget what the rabbit's name was. The tablecloth trick. Good stuff. So that's it. Hopefully you found that helpful.